Hello and welcome to Analog Electronics and Physics Lab 11, Reactive Networks Part 3, the last of the non-VAM orientated labs this year. We'll be mostly looking at a series RLC circuit in this lab. That's a circuit which has a resistor, a capacitor and an inductor in series. In other words, it looks something like this. I've drawn this circuit where we're taking the voltage out as the voltage across the capacitor, but by changing the order of the components, you could take the output voltage as the voltage across the resistor or the voltage across the inductor, depending on what circuit you wanted to build. But we're going to start out by taking the output voltage across the capacitor. Now, one important point, probably the most important point to realize about this circuit, is that it has a resonant frequency. And what I mean by a resonant frequency is a frequency at which the impedance of the inductor and the impedance of the capacitor cancel out. If you remember, the impedance of an inductor is j omega L. The impedance of a capacitor is 1 over j omega c, which I can write as minus j over omega c. So if you think about that on an argand diagram, the impedance of an inductor starts off at low frequencies at a very low positive imaginary value, somewhere around here perhaps, and as the frequency increases, the impedance of the inductor will increase up the imaginary axis. However, at very low frequencies, the impedance of the capacitor is a very high value and it's negative imaginary. So it would start off all the way down here, and as the frequency increases, the magnitude of this impedance will decrease, but it will remain negative imaginary. It will start moving up here at higher frequencies. Now, as this moves up and this moves up as well, there will be one frequency at which the magnitude of the impedance of the inductance and the magnitude of the impedance of the capacitance are equal. And at that particular frequency, we would have the magnitude of the impedance of the inductance equaling the magnitude of the impedance of the capacitance, which just means that omega L equals 1 over omega c, or omega equals 1 over the square root of LC. And that's called the resonant frequency, usually indicated by a small 0 below the W. That is an interesting frequency, because at that frequency, the impedance of the inductance and capacitance cancel out, so the only impedance left in this circuit is the impedance due to the resistance, which is independent of frequency. And if we have a total impedance in our circuit which now has the minimum possible value, it's just equal to R, then the current through our circuit is going to be a maximum as well. There are several properties, therefore, of a circuit when it's at this resonant frequency. And each of these can be used in the lab to determine whether you are at the resonant frequency. First one I've got in the slide here is that the resonant current and voltage are going to be in phase. That's the voltage input here and the current that's flowing in through this resistance, the input current. They are going to be in phase because the only impedance in this network is due to the resistor, and the resistor does not have an imaginary component to its complex impedance. It's just a resistance. The voltage and the current are in phase. That's what Ohm's law tells us. We've also got a maximum current because we have a minimum impedance in our circuit. The third one here isn't exactly true, but it's a very good approximation, particularly for circuits with a high Q value. The voltage across the capacitor, which is our output voltage here, will be very close to a maximum. And why would that be true? Well, because we have a maximum current flowing through our circuit. And if there's a maximum current flowing through our circuit, then the voltage that's generated across the capacitor will be that maximum current times the impedance of the capacitor, which will be close to the maximum possible voltage that you can get out across your capacitor. So that's a good way of determining whether you are at the resonant frequency in the lab. Change the frequency until the output voltage across that capacitor is at a maximum. Another way to do it is to measure the voltage across the capacitor and the inductor. So the voltage at this point here in the circuit. Because there, the output voltage should be a minimum. Because effectively, that point there is almost connected directly to ground. Remember, the impedance of the inductor and the impedance of the capacitor are cancelling out, so the point there has a very low impedance between it and ground, which means that there will be a very low voltage there as well. And that only happens at the resonant frequency. You'll never get an absolute zero voltage out of this circuit if you look at that point there, because real inductors, as you may remember from an earlier lab, aren't very good in the sense that they have a significant parasitic resistance as well, which doesn't go away at the resonant frequency. And you can see this kind of thing happening in the simulator, as you will with the real circuit. At this frequency of 1 kHz, we are not at resonance. There is a 1 volt voltage across the capacitor, but almost no voltage across the inductor at all. And if we were at the resonant frequency, with the impedance of the capacitor equal and opposite to the impedance of the inductor, then the magnitude of the voltage across the capacitor would be equal to the magnitude of the voltage across the inductor, and that's clearly not happening. One of them is a volt, and the other one is 13.03 microvolts. So let's change the frequency. And we'll go up. And you'll see that as we get to higher frequencies, the voltage across the capacitor and the voltage across the inductor are both increasing. And if we get too close to the resonant frequency, which is round about there, we're getting quite large voltages across the capacitance and the inductance. They're not quite equal. If we were exactly at resonance, they would be equal. So it's very close to there. But you can work out what the resonant frequency is using the formula derived before. Do remember, of course, that the capacitors and inductors that you use in the lab will have a fairly wide tolerance of 10% each or so the resonant frequency that you measure with your real components won't be the same as the ideal resonant frequency that the simulator suggests. We can also make bandpass filters with inductors and bandpass filters with quite high Q factors. And you may remember from the lectures that the maximum gain of one of these bandpass filters is always 0 dB, at least in theory with ideal components, but the bandwidth is a function of the Q factor. And we need to tighten up our definition of bandwidth here. The 3 dB bandwidth is the range of frequencies in which the gain is within 3 dBs of its maximum. So with this type of amplitude response here, this is the 3 dB bandwidth, from this frequency to this frequency, that range. Now, just a reminder of definitions of Q factor. It comes originally from this form of writing the denominator of a second order frequency response. But for a bandpass filter, the Q can also be determined by taking the center frequency and dividing by the 3 dB bandwidth. For a low-pass filter, or indeed for a high-pass filter, where the output is taken across the capacitor or across the inductor, then the Q is equal to the gain at the resonant frequency, and that's the voltage gain, not the gain in dBs. There's another formula for Q, which we haven't talked about in the lectures yet, but we'll come back to in the next lab, which says that Q is related to the ratio of the energy stored in the network. Now, remember, capacitors store energy in the electric fields and inductors store energy in the magnetic fields. That's stored energy. But they also dissipate energy per cycle because some current is flowing through that resistor. And the current flowing through that resistor generates heat, and that's energy lost. The ratio of the energy stored in the electric and magnetic fields in the capacitor and inductor to the energy dissipated in the resistor, that's another way in which you can determine the value of Q. Okay, some tips and reminders for this lab. Do remember, the scope probes measure the voltage between 1 point and ground, and it has to be between 1 point and ground. So if you want to measure the voltage across the resistor, the voltage across the inductor, and the voltage across the capacitor all at the same time, you can't. The easiest way around that is to just swap the order of the components in the circuit. The current will be the same, and therefore the voltage across the components will be the same, because the total impedance in the network is the same. It doesn't matter which order the components are in, the total impedance of the series combination will be the same. So you can just swap the order of the components. Whichever component you want to measure the output across, make sure that one lead of that component is connected to ground, and then this scope can simply measure the voltage directly across that component. Another point this lab, we're going to be taking, certainly near the resonant frequency, some quite large currents out of the function generator, which means that you cannot assume that the output of the function generator is going to be constant. It won't, because there is this 50 ohm output impedance built in to the function generator. And as the current changes through the network, the voltage drop across that internal resistance inside the function generator will change as well. So to work out So to plot the amplitude response of your filters, you'll have to constantly measure the input voltage as well as the output voltage of your network, because the input voltage will keep changing, particularly near the resonant frequency. Finally, very important in this lab to take your measurements using a ×10 oscilloscope probe. A ×1 oscilloscope probe effectively looks like a 1 megohm resistance, which isn't so much of a problem, but also a 50 picofarad capacitor in parallel with whatever you're trying to measure over. And that can disrupt the behavior of the circuit. It's something that's worth trying in the simulator, just to see how big an effect this can be, especially at the higher frequencies. Also note that most of this additional capacitance doesn't come from the oscilloscope itself, it comes from the cable connecting the probe to the oscilloscope. Just that length of cable has an appreciable capacitance. So if you're using one of the breadboard utility thingies, then don't use the probes with a length of coax cable attached to them. As soon as you connect up one of those to your circuit, you are in effect adding several tens of picofarads to your circuit, and that can disrupt its behavior. So, ×10 scope probe and connect it directly to the leads of the components that you're trying to measure. That's all I wanted to say this time. Good luck.